Hi everyone. Let us discuss this example of partial derivative. We have this function, we have to find its derivative with respect to x and with respect to y at point 0, 0. We are going to use definition of partial derivative to find their derivatives. Okay, so let us start. So clearly I will mention by definition. Okay, so by definition, deba f by deba x at point 0, 0. Okay, so definition says limit h tends to 0 f of 0 plus h comma 0 minus f of 0 0 divided by h. See, here we are finding derivative with respect to x with respect to first component. So that's why I added h only in first component. Okay, so let us solve. So limit h tends to 0 f of 0 plus h 0 minus f of 0 0 divided by h. So this is equal to limit h tends to 0 f of h comma 0. So this definition we have to use to find its value. So here you can easily see x is equal to h and y is equal to 0. So let us put those values here. So we'll have h square divided by root h square plus 0 square means 0 minus f of 0 0. See, when we have 0 0, if both of them are 0, that time we have to use second definition for value of f is 0. So clearly I will mention 0 divided by h. See, we can do one thing. This h square, that means 2h are there. So we can cancel one h with this h. So therefore, limit h tends to 0. I am cancelling one h. Okay, so h upon root. What we are getting? H square. Okay, so maybe you are thinking square and square root will get cancelled and we will have h. No. See, square and square root will get cancelled, but that square root always give us positive value. So that's why I supposed to write here, just a minute, this is equal to limit h tends to 0 h upon mod h. Since it always returns us positive value, so square and square root will get cancelled, but we will have mod h. So what will happen if mod h, if h is positive, h will get cancelled, we will have 1, but h is negative. So that means what I want to say, limit h tends to 0 h upon mod h means plus minus h. So they will get cancelled and we will have plus minus 1. Getting? So that means value of limit is either plus 1 or value of limit is or minus 1. Okay, but if limit exists, its value should be unique and we are getting two different values, 1 and minus 1. So therefore this limit does not exist. So I'll mention there this limit, I will clearly mention this limit does not exist. So therefore deba f by deba x, that means this partial derivative deba f by deba x at 0 0 does not exist. Okay, so in this way we proved that this partial derivative does not exist. After that, okay, after that we will try for deba f by deba y at 0 0. But before that I will suggest you to make screenshot of it and after that we will go further. Okay, so let us find second partial derivative, that is deba f by deba y. So deba f by deba y at 0 0. So definition says limit h tends to 0 f of 0 comma 0 plus h minus f of 0 0 divided by h. See, here we are differentiating with respect to y, that means second component. So that's why I added h only in second component. So let us see what will happen. Limit h tends to 0 f of 0 comma h minus f of 0 comma 0 upon h. Limit h tends to 0. So let us find its value. F of 0 comma h. We have to use this definition to find its value. But here x is 0 and y is h. Let us put their values. So 0 square, getting x is 0. So 0 square 0 upon 0 plus h square minus f of 0 0. As I told you earlier, that means if both of them are 0, we have to follow second definition. That means it's 0 divided by h. So this is equal to limit h tends to 0, 0 upon anything we will have 0. So 0 minus 0 divided by h. Obviously its value will be 0 since numerator is 0. That means partial derivative with respect to x does not exist, but partial derivative with respect to y at 0, 0 exists and its value is 0. Okay, so this problem is over here. You can make screenshot of it, and after that we will go for one more problem. Okay, let us discuss this second example. We have this function and we have to find its partial derivative with respect to x, with respect to y at point 0, 0. Let us follow the definition again. So I will mention by definition. See, definition says deba f by deba x at 0, 0. You can also easily tell the definition. Definition is limit h tends to 0 f of 0 plus h 0 minus f of 0, 0 divided by h. This is equal to limit h tends to 0, f of 0 plus h is h, 0 minus f of 0, 0 divided by h. So now we have to use this definition to find their values, right? See, it has two distinct definitions. If product of x and y is non-zero, we have to follow the first definition. But if product of x and y is 0, then we have to follow the second definition, which is simply 0. Here, what is x? H. What is y? 0. What is their product? X into y. H into 0, 0. So that's why I should follow the second definition. If it is non-zero, then only we should go for first definition. So this is equal to limit h tends to 0. So here we are having a product 0. So I should follow the second definition, which is 0 minus here also we have a product 0, 0 into 0, 0. So I should follow the second definition, 0 upon 0, 0 minus 0 upon h. So we will have obviously 0. So in this way we can say partial derivative with respect to x exists at 0, 0. Okay, and which is 0. So now I will go for partial derivative with respect to y. Now deba f by deba y at 0, 0. See, I am going to follow the definition. So limit h tends to 0 f of 0, 0 plus h minus f of 0, 0 divided by h is equal to limit h tends to 0 f of 0, 0 plus h minus f of 0, 0 divided by h. So limit h tends to 0. See, what is x here? 0. What is y? H. What is their product? 0 into h is 0. So that means I should follow the second definition again, and it gives us value 0. So 0. Here also 0 into 0, 0. So that's why by second definition value 0 divided by h. So obviously its value is 0. So that means in this case, in this problem, both partial derivative exist at 0, 0 and both of them are 0. Okay, both of them have having value 0. So you can make a screenshot of it, and after that we will stop. Thank you. Bye bye.